Good morning.
Morning.
All right. Any questions? Okay. So let's keep talking about gases and gas laws. And yesterday we talked about the pressure volume relationship for gases, and then we talked about the volume temperature. Now what I want to do is I want to talk about the relationship between volume and moles. Okay. So if you think about it, if you have a balloon, so you close off this balloon. Let's say you put a mole of a gas in there. So remember, a mole is an amount. Essentially what's observed is that if you put in more gas into the balloon gets larger, right? So let's say we got 2 moles. Okay. So what that tells us is that the volume of a gas, volume of a gas is proportional to the number of moles of the gas. Okay, so this can be written a couple different ways. One way is like this, V1N1 equals V2 over N2. And again, the V refers to the volume of the gas. Typically, the volume of the gas is the same as the volume of the container. All right. So if they say the volume of the container is 2.5 liters, what they mean is the volume of the gas is 2.5 liters. And then N is the number, not of grams, but number of moles of the gas. Okay. Now, what's observed when we look at gaseous reactions is if you take an equation, I'm going to take this one right here, 2H2 plus O2. Let's make the reactants gases, and I'll make the product a liquid. Okay, so there's your balanced equation. We can interpret this equation as in the following way. We can say that 2 moles of H2 react with 1 mole of O2. Okay, so we're using the coefficients as ratios to indicate how much of one substance will react with another. So we could write this as 2 moles of H2 for every 1 mole of O2. Okay. Now, what's significant about that in terms of the properties of gases, since those are gases, is that we can take this relationship here. By the way, this one's called Avogadro's law. Okay, that relationship between volume and moles is that we can do the following. We can make a proportion out of that and say that the volume of H2 is related to the volume of O2. And the ratio here is 2 to 1. So what that means is the volume of H2 will equal 2 times the volume of O2. Okay. So it's twice as much volume of H2 as there is volume of O2. So let me show you an example of how this works. It's a relatively simple relationship. Let me save this one. Okay, suppose we have methane gas And I'm going to write the chemical formula here, CH4. Oops. Reacts with chlorine gas, which is Cl2, to form hydrogen chloride gas. And carbon tetrachloride gas. What volume of carbon tetrachloride would be produced by this reaction if 1.24 milliliters of chlorine gas were used? Okay. So in order to answer this question, we need to know something about the equation. The previous reaction I showed you, I had the balanced equation, and I said the volumes were related to the balanced equation. The same is true here. So that means we need to write the balanced equation. So here are the two reactants, and then hydrogen chloride and carbon tetrachloride are the products. So two reactants, two products. So CH4 and Cl2 are the reactants. The products are hydrogen chloride, HCl, which you might recognize as hydrochloric acid. Hydrochloric acid as a pure substance is actually a gas. And carbon, tetra means four, so four chlorides, carbon tetrachloride, okay? So now we got to balance it. Looks like there's one carbon on the left and one on the right. There are four hydrogens on the left, but only one on the right. So I'm going to put a 4 in front of the HCl here. Okay, so our carbon and hydrogen are both balanced. Now we just have to do the chlorine. On the left side, there's 2 chlorines. On the right side, there's actually 8, right? Because you have 4 times 1. So that's equal to 4. And then you got a 4 here. So 4 plus 4 is 8. So if you have 2 over here and you have 8 on the right side, you need to multiply this by 4. Okay, and that's going to give us 8. So there's our balanced equation. Now we can do this relatively simply. The relationship they're curious about is chlorine gas. So they're telling us it's 1.24 milliliters of chlorine gas. And they want to know the volume of carbon tetrachloride. Okay, so this is the one they're interested in. And then this is the one that's given. Okay, so what you can do is you can set up a proportionality. What you do is you say the following. It's 4 moles of chlorine for every 1 mole of carbon tetrachloride, right? That's from the balanced equation. Or you could write it equally. You could put this one on top. Either one will work. Okay. And so this has got to be equal to the volume of the carbon tetrachloride divided by the volume of the chlorine. Okay. The volumes are proportional to the number of moles. If you double the number of moles, you double the volume. Okay. So what we want to know is we want to know the volume of carbon tetrachloride. So this relationship that I wrote here is possible, probably a little more easier or more relevant than this one, because this one has the carbon tetrachloride on the bottom. We want carbon tetrachloride, so we want to have carbon tetrachloride on the top, okay? So the ratio is essentially 1 to 4. So what we can do then is we can say, okay, the chlorine gas, we know that one, and that's 1.24 milliliters, okay? So the chlorine has to be 4 times as much as the carbon tetrachloride, 4 times as much, right? So what we do is we want to get carbon tetrachloride. So we're going to multiply both sides by the 1.24 milliliters. So 1 mole of carbon tetrachloride over 4 moles of chlorine times 1.24 milliliters. That's going to give you the volume of carbon tetrachloride. I'm just multiplying both sides by 1.24 so that I can get rid of the 1.24 on the right side and move it over to the left side. So if you do the arithmetic, that's about 0.31. Okay. And then you can kind of look and see if it makes sense. What we said was the volume is proportional to the number of moles. So if you have 4 moles of chlorine and you have 1.24 milliliters, then 1 mole of carbon tetrachloride should be 1/4, 1 over 4. So that would be 0.31 milliliters. Okay. So there you go. That's essentially the Avogadro's law problem. It's this relationship between volume and number of moles. Any question on that one? Okay. Let me save that one. And what I'd like to look at now is section 10.3, which is called the ideal gas law. Okay. Again, what's unique about gases compared to solids and liquids is that they actually obey these very simple mathematical relationships. So for example, if I take, a mole of hydrogen gas, which is bouncing around in a container, right? All these little atoms are bouncing around, or molecules, randomly bouncing off each other, bouncing off the walls of the container. Obeys very simple relationships. P1 V1 equals P2 V2, right? In other words, if I change the pressure of the hydrogen, it'll change the volume. This is our pressure volume relationship. V1 over T1 equals V2 over T2. This gives us a relationship between the volume and the temperature. If we heat the gas up, the volume will expand. And now we have this third one, which is V1 over N1 equals V2 over N2. If you look at solid, so if I took a mole of solid, 1 mole of ice, there is no simple equation to describe the properties of that ice. It's too complicated. So there's no what we call equations of state for a solid. Same is true for a liquid. Even if I took a mole of water, liquid water, there is no underlying equations that we can use to describe the properties of that liquid water. It only works with gases, mainly because of the nature of how they're organized. So what I'm going to do at this point is I'm going to take these 3 equations and I'm going to put them together. And so let me write them slightly differently. What I'm going to do is I'm going to say that the pressure of a gas is proportional to the volume of the gas. So not equal to, but proportional to. That's this one right here. The second relationship is the volume of a gas is proportional to the temperature of the gas. Remember, this has to be in Kelvin. Okay, and then the volume of a gas is proportional to the number of moles of the gas. Now, there are some requirements for these relationships to be true. This one requires, this is our assumption, that the temperature and the number of moles are constant. This one requires that the pressure and the number of moles are constant. And this one requires that the pressure and the temperature are constant. And that might not be the case. So what we have to do is we have to take into consideration that there are actually 1, 2, 3, 4 different variables in the properties of gases. 4 different variables. So let's put all those variables together, and here's what you end up with. The pressure of the gas times the volume of the gas is proportional to the number of moles of gas times the temperature of the gas. Now, this is only a proportionality. If we want to make it a constant, if we want to make it an equation, we have to put a constant in there. So we'll slip a constant in there to make it an equation. PV equals K N T, where K is a constant. That means it doesn't change. Typically, this is the constant we use in R, and that's called the universal gas constant. Universal gas constant.
Why do you have to have a constant?
Because it'd be sort of like this. If I said, suppose I said that your weight is proportional to your height, meaning as you get taller, you get heavier. But we couldn't say that your weight is equal to your height, right? It doesn't make sense to say that someone who weighs 140 pounds is equal to 140 inches. It doesn't work that way. But we do know that your height affects your weight. As you get taller, you get heavier. So we would say they're proportional to each other. But what you could do, you could actually make an equation. That's what this thing called the body mass index. That essentially what it does is it turns a relationship into an equation. So what you do is you say weight is proportional to height. But it's not equal. But if you do this, if you slip a constant in there, K, times the height, then you can actually make an equation that allows you to predict the weight based on the height. So if I said, okay, you're 5 feet 11, now I know what your weight is. But you need to know what that constant is. So what you would do is you would run experiments to figure out the value of what that constant is. Okay. Here's another example. So this is a simple one, kind of trivial. You could say, oh, I know that your height in inches is proportional to your height in feet. That's true. In other words, if you get taller in terms of height, feet, you're also getting taller in terms of inches. That makes sense, right? But that doesn't mean that they're equal. You wouldn't say 60 inches equals 60 feet. So what do you need? You need a constant. So what you would do is you'd say this, your height in inches is equal to 1/12 times your height in feet. Oops, sorry, 12 times. So in other words, if you take your height in feet, 5 feet, multiply it by 12, that gives you 60 inches. Now you know what your height in inches is. So you need that constant to take a proportionality and make them equal to each other. So typically the symbol that we use in this relationship over here is R, not K, but R. K can be used, but it's in a specific context. So you may see it in textbooks and stuff, but R is the one we're going to use. And for some reason, I don't know why, it's historical for some reason. Instead of putting the R in the front, they put it in between the N and the T. Not sure why. And this, what it does is it gives us an equation that relates all 4 of these variables. So these are called variables. All 4 of those are called variables. And this one is called a constant. Okay. This equation altogether is referred to as the ideal gas law. And the term ideal, it's a deep meaning of that word. In this context, the word ideal means that this equation can accurately predict the behavior of a gas under certain conditions, meaning it's not a perfect equation. It's not always true. It's true under certain conditions, which we call ideal conditions. Okay, so let me talk about this equation, and then I'll show you a couple of examples with it. This PV equals nRT, the ideal gas law. Generally, it works, meaning that it will accurately make predictions for you at high temperature and low pressure. Now, it's questionable. What do you mean by high temperature and low pressure? Typically, what we mean is if the temperature is approximately 0 Kelvin, it won't work. Meaning if it's close to 0, this equation is not going to work. And the reason for that is that when you get to low temperatures, things start to behave like liquids. And if they start to behave like liquids, these gas laws don't work anymore. They only work for gases. So low temperatures don't really work very well. High pressure. So if I say the pressure is, much greater than an atmosphere, it's not going to work. So when you look at these problems, and what happens is when the pressures are really high, really what's happening is the atoms are getting very close to each other. So again, they start to behave like liquids and solids. So it's just not going to work anymore. If you try to use this equation on the surface of the sun, for example, it's probably not going to work because the pressure of the hydrogen gases at the surface of the sun are so enormous. They're so close to each other. It's hard to actually even think of it as a gas. It is a gas, but it's a very unusual type of gas. Likewise, if you're building a probe that's going to go through the atmosphere of Jupiter and dive into the atmosphere of Jupiter, where the pressures might be hundreds of atmospheres or thousands of atmospheres, it's not going to work. This equation just won't function properly. So when you look at the problems, what you're going to find is you're going to see temperatures that might be 200 Kelvin, 300 Kelvin, 250 Kelvin. Those are higher temperatures. And you're going to see pressures that might be an atmosphere or half an atmosphere, maybe 2 or 3 atmospheres, but you're not going to see 1,000 atmospheres because at that pressure, gases are going to start behaving like liquids. And at really low temperatures near 0 Kelvin, that might be like 50 Kelvin, they start to behave like liquids as well. Okay, so it puts some limits on that. So that's why we call it ideal. It only works under some specific circumstances. Likewise, there's some gases that really don't obey it very well at all, like water, for example. Water, the molecules are so strongly attracted to each other via hydrogen bonding that it's hard to even get the ideal gas law to work that well with water, even at a reasonable temperature and pressure. Okay, so at some point it becomes an approximation. So that's called the ideal gas law. The value of R you can get confused by it. There are different values for R. With different units. Most typically, the value you're going to use for R, by the way, again, I'll remind you on this. This is called the universal gas constant. Universal meaning that you can use it no matter what the gas is. You can use it for O2, H2, N2. You don't need a different value for each gas. So this is the most common value that you'll use in your calculations. 0.08257, and then the units are atmosphere liters per mole Kelvin. It has a lot of units in it because this equation has so many quantities, so many variables in it. Okay, that's the most common. But you will see some problems where it's different, where it's 8.314 joules per mole Kelvin. This is less common, but you will see it. And then it's not uncommon also to put this in kilojoules, 0.008314. This is essentially just a modification of the second one, kilojoules per mole Kelvin. So we just divided it by 1,000. So this one's even less common. Now, I do want to point out, you will see that there's joules in that. And remember, joules is energy, right? That's the unit of energy. So that means gases, in some sense, are connected to energy. And it turns out they are. Here's what I'm going to claim. P times V is proportional to energy. And since PV equals nRT, that means that nRT is proportional to energy. So the larger P times V is, the more energy a gas has. So if I take a gas and I put it at a high P and a high V, it has more energy than a gas at low P and low V. It will have less energy. Okay. So that's an interesting aspect of gases. The amount of energy the gas has is proportional to the pressure times the volume, or proportional to nRT, the temperature of the gas. Okay. Ideal gas law, like I said, this is the most common value you'll use, but there are a couple problems, I believe, where you have to use this one here. I'm not sure if there's anywhere you use this value, but you can usually just use dimensional analysis to figure that out. So let me show you an example. There's essentially two types of problems. Well, actually, I take it back. There's three types of problems that you do with the ideal gas law in this course. Okay, so let me show you the first one. Carbon monoxide gas carbon monoxide is CO2. I'm sorry, CO. Is collected at negative 6.0 degrees C in a flask with a volume of 40.0 liters. Okay. The pressure of the flask, actually, I should say the pressure in the flask, is 0.400 atmosphere. Calculate the number of moles of CO gas and the mass of CO. in the flask. Okay, CO, carbon monoxide. You've probably heard of carbon monoxide. It is related to carbon dioxide. It is a gas that is produced when you burn fuel inefficiently, meaning that you don't get the mixture of oxygen and fuel right. And what happens is carbon monoxide is produced instead of carbon dioxide. And carbon monoxide is a very dangerous gas because what happens is hemoglobin, which is the blood that, which is in blood, and we use that to transport oxygen and carbon dioxide out of the body, into and out of the body. Carbon monoxide will actually bind to the iron atom in hemoglobin, but it binds in a way that makes it irreversible. In other words, it chemically reacts with the iron and cannot be released by the body. So it essentially keeps the hemoglobin from being able to transport oxygen or carbon dioxide. So it's a pretty dangerous gas. So here's what we're told about the carbon monoxide. So we know it's carbon monoxide. That's our chemical formula. So that's the first piece of information we have. The second one is we're told the temperature of the gas. The third piece of information we're given is that the volume is 40 liters. Okay. And then the fourth piece of information we're given is that the pressure is 0.400 atmosphere. And then we're asked to find the number of moles. Okay. So if you take a look at this particular problem, we're told T, V, and P. The ideal gas law looks like this, PV equals nRT. So what we know is the pressure, the volume, and the temperature, and we're asked to find the number of moles. Okay. So how do we do that? Well, we want to have the number of moles. So what I'm going to do is I'm going to do the algebra over here. We want N all by itself. So what I'm going to do is I'm going to divide by R to get rid of R. I'm going to divide by T to get rid of T, and that'll give me N. But again, you have to do that on both sides. Okay. So P times V over R times T is equal to N. Make sure you're careful when you use your calculator for these problems. When you divide by RT, make sure you divide by R and then divide by T. Don't divide by R times T on your calculator, because if you do it that way, the calculator may interpret it as divided by R, but times T instead of divided by T. You want to divide it by R and divide it by T, okay? R we know is a constant. That's the 0.08206, 2057. And then we've got all of the other quantities in here. So let me do the calculation over here. PV over RT, so 0.400. I'm going to try to put the units in here. The volume is 40.0 liters. I'm going to make a little more space for this over here because R has a lot of units. R is 0.082057 atmosphere liters per mole Kelvin. And then T, remember, this is a gas law problem, so be very careful. The temperature cannot be in degrees C. We need to convert that to Kelvin. Talked about that yesterday, right? So that means our temperature, what you do is you take your minus 6.0 and you add your 273.15. And so you get 267.15 Kelvin. So there's your temperature in Kelvin, 267.15 Kelvin. Let me show you the unit, the dimensional analysis. Atmospheres over atmospheres, liters over liters, Kelvin over Kelvin. And now you have 1 divided by 1 over moles, right? You have 1 up here in terms of the units, and then over here it's 1 over moles. So that just gives you moles. Okay. So N, pretty straightforward. Let's see what that works out to. 0.4 times 40 divided by, oops, that's not right. 0.4 times 40 is 16 divided by 0.082057 divided by 267.15. And it looks like you get 0.729876144 moles. But of course, that's too many sig figs. So we come back and we say, okay, well, this one right here has 3 sig figs. This one has 3. This one has 5. This one has 5, although arguably, this one only went out to the tenths column. So arguably, we only know this to the tenths column. So that would be 4. But in any case, the ones that have 3 have the fewest sig figs. So we're going to round it to 3. So let's see, 7. Now, here's what we do. 1, 2, 3. This one's 5 or greater, so that rounds that up to a 10. If you round that up to a 10, that rounds that up to a 3. So 730. And that would be 3 sig figs. Okay, that looks pretty good right there. And then the next issue is that how do we find the mass? We also want to find the mass of CO in the flask. Well, it's carbon monoxide. If we know the number of moles and we know the chemical formula, we can figure out the number of grams quite easily. We calculate the molar mass. The molar mass would be, there's 1 carbon, so 1 times 12.01, 1 oxygen, 16.00. So this gives us 28.01 grams per mole. That's the molar mass. So then we do a mole to mass conversion. 28.01 grams for every 1 mole. Okay, so 0.730 times 28.01, and you get 20.44. That's too many sig figs. Again, we've only got justified 3 sig figs here. Either of these is 3. So we got to round that. 20. That's our 3rd sig fig. This one's less than 5, so we just truncate it. And there you go. So 20 grams, 20.4 grams. Okay. So that's the first type of use of the period of the ideal gas law. You're using the P, the V, the N, the R, the T. You know the value of R. Generally, they're going to give you 3 of the values. They're going to give you PVT or PVN or VNT, and you find the 4th one by manipulating the equation. Remember, make sure the temperature when you do these calculations is in Kelvin, not in degrees C. It will give you the incorrect answer if you use degrees C. Okay, any questions about that one? Okay. All right, let me show you now another relationship, and this one involves density. It's kind of a fun issue. Okay, and this is relating the density of a gas and the molar mass of the gas. Okay, so I'm going to use D for density. I will point out that you will see in certain references, sometimes you see the letter rho. This is not a P, it's a rho. It's the Greek letter R. Sometimes that's used. but this is the one that we'll use, D for density. Molar mass. Now, I don't remember if I even gave you a symbol for molar mass back in chapter 3. Typically, the symbol for molar mass is an uppercase script M. So I'll draw it like that. Okay. Some references will use capital M, molar mass. Sometimes this is used. I'm going to use this one here. So I'll use D for density and then the script capital M, uppercase M for molar mass. Now, essentially what happens is this. If you think about a gas, the gas is in a container, so it has a volume. You've got all those little molecules bouncing around in the container. Each one is tiny, but there are so many of them that it adds up to significant pressures and forces. In fact, if you've flown in an airplane, you can kind of sense the nature of the pressure of a gas. If once you start rising in altitude, often the atmospheric conditions in the plane will change. The pressure, the air pressure will change. The technology they have in these planes is pretty good. It keeps the pressure relatively constant, but typically it'll go down by about 20%, 20 to 30%. And you can feel that in your ear. You'll feel your ear pop. You'll feel your sinuses reacting to that. So we're very sensitive to the pressure of these gases in the air. So if we take a look at that gas, it's going to have a mass, right? If you have material, you have a mass. And then, so what would we say? We would say that the density of the gas is just whatever that mass is, M for mass, divided by whatever that volume is, V, right? So a gas has a density. It's just how much is in there, how much it weighs, divided by whatever the volume of the container is. Now, that same gas also has a molar mass, right? So for example, if I were to say that this is carbon monoxide gas, we know that the molar mass is equal, we just did that, 28.01 grams per mole, right? What that means is if you have a mole, 6 times 10 to the 23rd molecules, the mass would be 28.01 grams, right? So I could, for this problem, I could say, look, suppose I have a mole. That means we would have 28.01 grams of this carbon monoxide. So there's a molar mass as well. But since it's a gas, there's also another equation, right? PV equals nRT. This is valid for gases. So that means we've actually got 3 relationships we can play around with: the density, the molar mass, and the ideal gas loss. So let's look at the molar mass in a little more detail. What do we mean by molar mass? We get very good at calculating it on the periodic table. We take, we look it up, we add up the molar masses of each element, we put them together, and we got the molar mass of the substance, of the compound. But the molar mass is really, more broadly speaking, it's the mass of the gas, it's the mass of a substance divided by the number of moles of the substance, right? That's what it is, really. It's just the mass over the moles. So if I said a gas has a mass of 88 grams when there are 2 moles, the molar mass would be the 88 grams divided by the 2 moles. And so that would give you 44 grams per mole. That's really, in a sense, what molar mass is. It's the mass of the substance divided by the number of moles. So what I'm going to do is I'm going to show you how we can relate these three equations and put them together into one. And I'm not going to show you how I do this because I've got videos you can watch on YouTube and it takes a while. So I'm just going to show you the result. For a gas, the molar mass of the gas is equal to the density of the gas times the gas constant, R, times the temperature of the gas divided by the pressure of the gas. And this is a nice relationship. What it does is it allows us to relate the density of a gas and its molar mass. The molar mass, in a sense, tells us what gas it is. If it's 44 grams per mole, that tells us it's carbon dioxide. If it's 28 grams per mole, that tells us it's carbon monoxide. So the molar mass can essentially tell us what gas we're dealing with. So this is the one we're going to work with in this example. The molar mass of the gas is equal to the density times the gas constant times the temperature divided by the pressure of the gas.
Sir, sorry for interrupting. Somebody is in the waiting room, and
Oh, thank you for letting me
somebody-
know. Yeah, do that anytime you can. Thank you. Because when I switch over, it's hard for me to see it. Thank you. Okay. All right. So let's take a look at a problem involving this relationship. So let me write it down again. The molar mass is equal to dRT. And before I actually do the problem, I'm going to show you the other relationship, which is sometimes we want to know what the density is and not the molar mass. So if you want to know what the density is, we need to relate it. So what I'll do is I'll multiply both sides by P. And so P over P is 1. And that gives us P times molar mass equals dRT. And then I'm going to divide both sides by RT. So that gives us the density relationship. So we have 2 now. Molar mass equals dRT over P. And density equals pressure times molar mass over RT. So depending on which one they're asking you for, if they're asking you for density, use the second one. If they're asking you for molar mass, use the first one. Typically those are the 2 relationships. So let's take a look at an example. An unknown compound. So if they tell us it's an unknown compound, that means we do not know its molar mass. You can't know what the molar mass of an unknown compound is, but this problem will allow us to figure out what's going on. So you got an unknown compound. It's vaporized at, okay, so let me write it down. An unknown compound is vaporized. Now, vaporized means it's converted into a gas. Okay, it's vaporized at 200 degrees C. The gas produced has a volume of 1020 milliliters at 1.00 atm. It weighs 2.49 grams. Okay. Find the molar mass of the gas or of the compound. Okay. So you'll recognize that this problem is a little bit different than the first one we had because here they're giving you the mass, but some of it is similar, right? In the previous problem, they gave us the volume. Here you're given the volume. In the previous problem, you were given the, actually, I think we tried to find the pressure. No, we had to find the pressure. So similar with this one. So there are some quantities that are the same, but notice it's saying find the molar mass. If you're doing a gas problem and it says to find the molar mass, that's this one right here. If you're doing a gas problem and it says to find the density, that's this problem right here, or this equation right there. So we do know what we're looking for. We're looking for the molar mass. So to find the molar mass, what do we need? We need the density, we need R, we need T, and we need P. Well, we don't have the density. I don't see density given anywhere in here. And typically when you do these problems, they don't give you the density, but you can figure it out. Here's how. The density of any substance is its mass over the volume. So if you have the mass, here it is, and you have the volume, here it is, you've got the density, right? So even though we're not given the density, we can calculate it from the mass and the volume, okay? R is a constant, so we know the value of R, 0.082057 atmosphere liters per mole Kelvin. So that's cool. Temperature, oh, here we go, 200 degrees C. Now I'm actually going to go ahead and add 273.15 because we know that when we're dealing with gas law problems, we can't have it in Celsius. It's got to be in Kelvin. So it's nice just to kind of knock that out immediately. Okay. And then pressure. The pressure is given, luckily, 1 atmosphere. Okay, so it looks like we've got almost everything set up here for the molar mass. There is one issue, and be careful about that. The issue here, this will trip you up on Alex. This is in milliliters, but this one here is in liters. That's a problem, okay? That's a problem because when you start canceling out the units, you're going to have a milli in there, and you don't want to have a milli in there. So what I'm going to do is I'm going to take this volume, which is 1020 milliliters, and I'm going to convert that to liters, just so that we don't have that problem. So 1020, remember from chapter 4, it's 1 liter is 1,000 milliliters. Common mistake is people put 100. It's not 100. 100 is used for percentages or centi, but the milliliter liter conversion is 1,000. So this gives you 1.020 liters. Okay, now that's a little bit better. So now let's calculate our density. 2.49 grams over 1.020 liters. Interestingly enough, that's pretty close to the density of seawater. 2.49 divided by 1.020, and I get 2. I'm going to leave an extra sig fig in there, 2.441 grams per liter. Just going to leave, this only has 3, but I'm going to leave 1 extra because we're going to do an additional step, another calculation with that number. So we don't want to do rounding errors. So density, 2.441. I don't really have much room in there to put the units, but I'll try. Grams per liter. Okay, now let's do R, 0.082057 atmosphere liters per k-mole. Sorry if that's kind of scrunched, but you know what the value of R is. We looked at that. And then the temperature, I've already gotten that up to Kelvin, 473.15 Kelvin. Okay, so density RT, DRT, dirt. Then we're going to divide that by the pressure. Pressure is 1 atmosphere. Okay, now I scrunched all that in there. And so here's what happens in terms of the units. This is, it's hard for you to see it, I understand. This is atmospheres up there and down there, so they cancel. Liters is down here and it's up here, so that cancels. Kelvin is up here and it's down there, so that cancels. So you're just left with grams over moles. And that's what you want, right? Molar mass is grams per mole. So that looks good. And now think about molar mass. Molar mass, there's a limit, right? We can't have a molar mass less than 1 because the molar mass of hydrogen is 1.01 grams per mole. So there's nothing in terms of the matter that we deal with in chemistry where the molar mass would be less than 1. It's got to be at least 1. Hydrogen, elemental hydrogen is 1. But remember, even in nature, hydrogen is really H2. So that actually the lowest value you can get is 2. So if you get anything below 2, there's probably something wrong here. Okay. So let's, and then the other issue is that when things get really, really heavy, they tend to form liquids and solids. So you're not going to see a molar mass of 1,000 or 2,000. Really, the highest molar mass I've ever seen for gas outside of exotic experiments is 350. About 350 is the highest I've ever seen. Okay, so you're probably not going to see anything above that. So let's go through the calculation. It's 2.441. Oops. 2.441 times 0.082057 times 473.15 divided by 1. And the number of sig figs, you got 3 here, you got 3 here, you got 3 here. You're not going to have more than 3 sig figs. So let's round it to 3 sig figs. So 94.7725. I'm going to round that to 3 sig figs. 1, 2, 3. 94 point. Now the number that comes after this first 7 is a 7 as well. So that means you round it up to 8. And there you go, 94.8. Now, I don't know what that gas is, to be honest with you. I don't know what weighs 95. It could be something like BR2 maybe. I think that might even be a little bit too heavy. So I'm not sure what it is, but 94.7. So it's definitely within our range of 1 to 350 grams per mole. So it could conceivably be a gas. It seems reasonable. Okay. That is essentially the second type of problem that you're going to see in section 10.3. Okay, which is molar mass density. So we're moving right along. What we want to do next is look at chemical reactions. This is all very static. We're just calculating amounts of materials, but we're going to start looking at chemical reactions tomorrow. So we'll do that. And then on Thursday, I guess, we'll look at the kinetic molecular theory. So we're looking pretty good here for chapter 10. Okay. All right. That pretty much ends it, I think. There's not enough time to go on to the next section. So I will say goodbye. And again, reach out to me today if you have any questions. I will start grading the third lab report today. So start looking for the scores to get added in today. It may take me till tomorrow, but I think I'll get finished done today. And so you'll have your third lab report in at the end of the day. All right. Have a great day, everybody.
Have a great one.
Thank you.
Bye. Thank you too.
All
Thank
right.
you.
Thanks for coming in and have a wonderful, wonderful day.